Hello, greetings. So in week 11, we set up some more complicated network shortest route problems. And so in this screencast, we're going to go through based on our setup work and solve them numerically using LibreOffice Calc. And so in this screencast, we'll look at parts 1 and 2, or parts 1 and 3, and then we'll have a separate screencast for part 2. And so basically in parts 1 and 3, what we did is we took our full network and we consolidated it so that when we had multiple routes on different airlines, we only wrote down the least expensive flight, since that would be the option we would choose. Right, and again, to put it in context, in parts 1 and 3, we're assuming that there's $0. It costs $0 to change airlines. Okay, so at a given airport, if you want to get to a given destination, you'll take the cheapest flight. Okay, so we created a consolidated network. Okay, and so we had all our variables here, right? And these are all of our possible routes. And so our variables will ultimately have values of 0 or 1. 1 if a route's taken, 0 otherwise. And then one note I want to point out is that in my original screencast, I had a small typo in my node balance for node B. And it should have been obvious to me because the way we have our notation, A is our starting node, and so our first index is our starting node. Our second index is your destination node, and so the second index here should have been B. So my apologies. So this variable shouldn't be XAC; it should be XCB. So our objective was to minimize our cost. Okay, here's all of our node balance constraints. And then we have our general constraints, basically forcing our variables to take on values of 0 or 1. Okay, so I'm going to jump over to Excel, or LibreOffice Calc. And what I've done so far is I've listed all of our variables, so all of our paths or routes. So then I give them initially a value of 1. So remember, solver is going to change the value of our variables to try and minimize our objective function. And so you need to start with an initial value. So I just gave them all initial values of 1. And then I list the cost. Okay. So next I'm going to list our objective, okay, which is going to be to minimize our cost. Okay. And that's here. All right. It's going to be the sum over all paths. The value of the variable times the cost of the path. Okay, well, remember the variable is going to have a value of 1 if the route's taken, 0 otherwise. Okay, and so I'm just going to use the sumProd function, or some product. So we're going to sum over all of our paths, and we're going to take the product of the value of that variable, which is either 1 or 0, times the cost. And next we list our constraints. Okay, and so I'm going to list my node balance for A, B, C, and D. Okay, and then I'm going to say in and out. Okay, so A, okay, what's going in is 1, so that's the initial unit entered in our network. Then I have AB plus AC plus AD. So it's basically all of our variables that begin with A, and it's this 1 or 0 variable. So AB, AC, and AD. Okay. Auto type there. When it comes to B, okay, what's going in is AB and CB, AB, and CB. So we're looking for variables with the second index of B. And coming out is BC and BD. So we're looking for all of our variables where the first index is B. So BC and BD. Oh, and I selected the wrong one. BC plus BD. Okay, then C, we have AC and BC. AC, BC. Okay, so all of our variables whose second index is C, and then on the right hand side, it's all of our variables whose first index is C. So we have CB plus CD. And then finally for D, it's all of the variables whose second index is D. So AD, BD, and CD. And the right-hand side is 1. So this is AD, BD, and CD. And the right-hand side is 1. Okay? And that's it, right? Our other constraints are essentially our constraints just requiring that our variables have values of 0 or 1. And so that'll just be that our variables are integer, non-negativity, so they're all greater than or equal to 0. And then we'll add less than or equal to 1. Okay, so we can readily add those. So to solve this, it'll be solver. Okay, so I'm going to minimize my cost by changing the value of my variables, right, which are going to be either 1 or 0. Okay. Now, in terms of our constraints, since these are all equalities, we can just do these all as a block. So my, in to each node has to equal my out to each node. Okay, and then in terms of non-negativity, right, we could do it via, a simple checking some extra features if we wanted to. Or alternatively, I can just highlight all my variables, and I can say they have to be less than or equal to 1. They need to be greater than or equal to 0. And they need to be integer. Okay. Notice there also is a binary option that requires them to be 1 or 0. But we'll keep it as such. Okay, so when I solve, we find that we should take, and let's look at our node. We're going to start at A, so we're going to take a flight from A to C, which costs $90. Then we are going to go from C to B, so we're going to go backwards. This flight that costs $30. And then we'll go from B to D. B to D. So we're going from A to C, C to B, and B to D is the cheapest route option. Okay, cool. So that is part 1, right? And the cost of going from A to C, C to B, then B to D is going to be $200. If you wanted to figure out exactly what airlines you were on, right, we could just track it we could map it back to our initial web. So if I was going from A to C, that's on airline X. Then going from C to B, that is on airline Z. And then going from B to D for $80, that's on airline Y. So you're starting on airline X, going to Z, and then going back to Y. Okay, so in the second problem, which we'll cover in a separate screencast, we'll account for having to pay for transfers, at which that may no longer be optimal. But here, when it's a $0 transfer, that's fine. Okay. All right. So now, if we were to look at we're going to look at part 3 here. So we're going to stick with this case of $0 transfer fees, but we're told that we can only tolerate at most 1 transfer. So put differently, add a constraint that the number of routes taken is at most 2. Okay. So remember, our variables take on values of 1 or 0. 1 if a route's taken, 0 otherwise. So if we are allowed at most 1 transfer, that means we can take up to 2 routes. So we can have at most 2 routes. And so we can add a constraint that the sum of our variables need to be less than or equal to 2. Right? That I can take at most 2 paths. Okay, so if I go back to my spreadsheet, I'm just going to copy this, and we'll call this part 3. Okay, so in part 3, if I go into solver, well, and actually let me create a sum variable. So let's do number of routes, and we could do this here. I'll list it as a constraint. So do number of routes. So our number of routes is going to be the sum of our variables. Okay, and that's going to be less than or equal to 2. All right, so C, in the previous solution, we had 3 routes or 2 transfers. So if I go back into Solver, all of our everything will be in there from our last case, which will be unchanged. And we're just going to add additional constraint that the number of routes is less than or equal to 2. So left-hand side is less than or equal to right-hand side. Okay, so when I solve for this case, looks like the price increases by $40. So the price goes up. So for comparison, from $200 to $240. And now the route is going from A to B and then B to D. So now I'm going from A to B. All right, I'm going from A to B at a cost of $160 and then from B to D. Okay, so at an increase of $40, right now I just have one single transfer in airport B or in node B. And so if we were to trace this back, I'm going to start on airline X and go from A to B. And then the flight from B to D would be on airline Y. So now I'm just going on airline X and airline Y. Okay, but fun. All right, that's it. And I'll have set up another screencast in which you look at part 2, which is a little more complicated, where there we're accounting for transfers or the non-$0 transfer fee between airlines. Okay, hope that helps.